football's sometimes the
Hi, everyone. Thanks for coming along to this ECM seminar. We're here today to celebrate the yearly award that the IMA does called the Graham Hoare Prize. And the Graham Hoare Prize is this annual award that is given to early career mathematicians who write in mathematics today. We have the 2023 winners with us today, Matthew and Brady, who are going to tell us about their article. They've expanded a lot on the article and they're going to fit in a lot of details for us. The article itself is available online, so you're welcome to go and read that at any point. So who am I? I'm your host today. My name is James. I'm a member of the Early Career Mathematicians Committee at the IMA. I used to be the events lead back in COVID times, and now I help them by running this seminar. We run maybe 5 or 6 seminars a year highlighting bits of work in the academic sector, mainly for those who are winning IMA awards. And you'll see a couple of seminars coming up hopefully soon. And I think on that note, I'm going to hand it over to Matthew and Brady. So you two, welcome. You're welcome to introduce yourself. And let's crack on. The other thing I should say is bandwidth is a bit troubling potentially at the moment. So if you're able to have cameras off and keep yourselves muted throughout the talk, that would be very helpful. Matthew and Brady, over to you.
Great, thanks, James. Yes, so thanks for the introduction. My name is Matthew, and Brady and I wrote this short article when we were PhD students together. We've since finished our PhDs, and so we're back to just talk you through the article that we wrote, and hopefully, give you a bit more insight and a bit more expansion on what we were saying in the article. But basically, this whole project is about trying to settle an argument and using a kind of an event or an external kind of process to settle an argument that we were having. I can't remember if it was where we were going for lunch or something like this, but basically Brady and I needed to decide what we were doing, and we wanted to try and come up with a way to make that decision. And so we decided to ask, can we use a football match to settle this decision? So yeah, where we'll go for lunch. And basically, we want this process to be kind of driven by an external event, so something we can't influence. So, maybe there's not a lot of trust, and, I don't know if Brady's going to be using a double-headed coin or something like this. So we thought, well, we have a passing interest in football. I think it was around the World Cup time, so World Cup feel was pretty high. But then we also want to try and make this kind of scenario be decisive. So if I said, we're going to bet on a football game, the typical response would be, oh, do you expect Reds or Blues to win, say? Which obviously doesn't work in this scenario because you could have a draw. And then there's also this concept of wanting it to feel fair. So if Reds were top of the league and Blues were bottom, then obviously you want to bet on Reds to win. Maybe you could say, oh, well, if it's a draw, Blues win, but it doesn't really necessarily feel fair. And so what felt fair to us, we can do some maths to see if it is fair, but what felt fair to us was to try and say, do we expect there to be an odd or even number of goals in a football match? So obviously, one person would bet on there being an even number of goals, one person would bet on there being an odd number of goals, and whoever won, say, gets to decide where to go for lunch. And so we can ask, can we model this mathematically? Can we decide if this is fair? I can't remember what the outcome was. I can't remember what the game we bet on, but this is a surefire way to basically make a decision. And so can we model this mathematically? Well, the straightforward way to do that is to say that you have some goal scoring rate in a match. And if you assume this is constant, you start to get a Poisson process, which is a very well-known process, and there's lots of statistics you can look up for that. And because we care about the total number of goals scored, so we don't care if it was a red goal or a blue goal, we can sum up the rates of those teams scoring together. So we get one total rate for goals scored in the match. And then the probability of there being n goals scored in a game is given by this formula, very convenient again, because it's this Poisson process. And so what we need to do to determine the probability of there being an even or odd number of goals is just to sum up over n for odd and sum up over n for even. And so we can do that. I'm going to write this out as follows. So the probability, of if you sum over all n, then obviously the probability is 1. So I'm going to write this like 1 equals all the purple terms. These are if there's an even number of goals. So 0, 0 we're counting as even. 1, 1 could be even. 2, 0, 0, 2. And then the green are the probability of there being an odd number of goals. And so you can write out these sums. You can sum up all the terms. And then depending on how much attention you paid in A-level maths, perhaps first year of university, you can probably spot that this second sum is pretty well known. And in fact, this is simply just the hyperbolic sine and cosine. So it has a really nice closed form solution. And this sum is easy to calculate, and it's easy to spot what's going on here. And we write them out in this exponential form with the 1 plus e, just to show that if you just look at these values, you can clearly see that the even probability of winning is always greater than the odd probability of winning. But we'll plot this just to kind of demonstrate. And so what we see is that because the probability of there being an even number of goals is always more than the probability of there being an odd number of goals, it's even better to be an even better. But it's interesting to think about how that changes and maybe try and get some intuition for this. So initially, if you expect there to be kind of a low goal scoring rate, so this is lambda, this is the x-axis. If we expect there to be, say, no goals scored in a football game, then obviously the score is always going to be 0, 0, which in our win condition means that there's an even win. So that's why the kind of the purple plot of the even winner starts at 1 for very low rate. But then if we have lots of goals being scored, then the distribution starts to spread out, and there's not really much difference in terms of the likelihood of an event between there being 59 or 60 goals scored. And so you start to lose that advantage, and the probabilities start to equilibrate and both be a half when you get to really high goal scoring rates, so to the right of the graph. But something that's quite interesting here, I think, is that if you look at when you expect there to be 1 goal scored in a game, then it's actually still more likely that there's an even number of goals scored. So even though you're expecting it to be 1, it's actually more likely to be an even number of goals than an odd number of goals when you evaluate this infinite sum. And so this was great. We thought this was a nice decisive way. It's quite a sneaky way to kind of trick someone, I guess, if you think, it sounds quite even, but actually there can be a bit of an advantage. But then, say the next day we want to go for lunch again and there's another person involved. Can we settle this argument if there's 3 people involved? So again, we have the same setup, but this time we want there to be 1 winner and 2 losers. And so what this means is that rather than having the odd and even win case, we say, well, let's think about the number of goals scored modulo 3. Is there remainder 0, remainder 1, or remainder 2? So if there was 0, 3, 6 goals scored, that would be player 0 wins. If there was 1, 4, 7, that would be player 1 wins. And if there was 5, if there was 2, 5, 8 goals scored, then that would be a player 2 win. And so rather than thinking about the parity in odd and even, we think about the remainder when you divide by 3. And so we go through the same process. We assume that it's this constant goal scoring rate, and we sum up all these terms. So the purple for the P0, which is the probability of the 0 player winning, the green and the blue. And then again, I don't think you could pay as much attention as you like in your A-level maths, but you're probably not going to recognize this sum. And I think that's because it's not really a standard sum. And so if we want to think about who's most likely to win in this situation, we're going to need to evaluate these sums, but they're not really standard. And it's also quite hard to generalize. So what if we had more people playing in the game, for example? And something that we realized was that you can actually, rather than thinking about the game as a whole and thinking about how many goals are scored throughout the game as a oneer, you can start to think about this as a dynamical process. So we can start to think about the goal scoring rate during the game. And so here's an example of a few different random games. So maybe you have this purple line where you have 1 goal scored at 20 minutes, or you have the green line where you get, in the middle of the game, there's quite a few goals scored. But here we can plot the fact that you actually have some goal scoring rate at every time. And so if we start to think about the odd and even game again, what this means is that this slightly modified rate, lambda tilde, this gives you the transition between there being an odd number of goals and an even number of goals. So the probability of player even winning actually changes throughout the time. So if I stopped the match, say at half time, I might expect there to be a different probability to at the end of the game. And you can write that as a differential equation. So you can say, well, what's the probability that there is an even win at some time t, and how does that evolve as the time changes? And from this kind of schematic, you can see that, well, because goals are scored at rate lambda tilde, then I'm having a flow of probability out of the even state that's proportional to the probability in the even state times lambda tilde. And then there's this flux of probability coming into that state from the odd state. And you can write this as a matrix equation where you have a vector p, which gives you the probability of each winning. And then you have this M matrix, this rate matrix, that gives you the kind of transitions in the system. And so what you can do is you can solve this equation, and you need to take the exponential of the transition rate and then also the initial conditions. So this is the initial score. And because we start with the 0, 0 case, that's always going to be at time t equals 0, probability 1 that there's an even number of goals, and probability 0 that there's an odd number of goals. And you evaluate this and you get exactly the same expression as before. You get this kind of cinch and cosh situation. And so it works. And so rather than thinking about the kind of doing this infinite sum, we can actually just evolve this system from some initial state and then see what it is at the end of the match. And so if we come back to the three-player case, where we have now, rather than just the odd and even case, we have the P0, P1, P2 win situations. The matrix looks really similar because you always have these transitions and these kind of flows in the system. But now the infinite sum that we couldn't evaluate before, we can now evaluate by, again, taking this matrix exponential and considering the initial state, which is that probability 1, P0 goals. And so this looks like this. We have this, the final probability vector looking like is given on the screen. And so we can solve this problem without having to evaluate these infinite sums if we actually just think about the way that the system evolves during the game, which I thought was really neat because you also effectively have evaluated the sum because those two quantities describe the same thing. And so you can evaluate these infinite sums by considering how the system evolves. Again, this is a bit harder to visualize than the two-player case. It's not so obvious just looking at this vector, who's most likely to win in each situation. And so we can again go to plot this. And if we plot the probability of each player winning versus the rate, we get a very similar plot as before. But interestingly, the zero remainder player doesn't always have an advantage. And so what we can say is that actually now the winner, who you want to be in this scenario depends on the goal scoring rate. So at low rates, you have the fact that there is a real advantage with being this zero remainder player. But very soon as you increase the rate, that advantage starts to go. And at some point, it's actually better to be the player that's betting on the remainder 1. And again, interestingly, even if you expect there to be 2 goals scored in a game, it's actually the lowest, it's the worst person to be in the bet to say, I expect there to be remainder 2 goals scored in the game, which again, I think is slightly counterintuitive. I think the plan is I'm now going to hand over to Brady. So hopefully this works. Okay.
All right. So we're going to go kind of one step farther. We're going to generalize to n players now. Oops. So the same sorts of assumptions we had before. We don't want any sort of external influence. We're going to base it on a football game, obviously. And we're going to have sort of 1 winner and n-1 losers now. And we're just going to sort of generalize what we did with the 3-player case. So we're going to look at the remainder when we divide by n. So as Matthew showed us the kind of matrix dynamical system, we're going to keep this sort of framework for the n-player case. So now we have n states, and every time a goal is scored, it sort of increments to the next one. And we can encapsulate that by this kind of heat map version of a matrix on the right. So the diagonal is just sort of minus lambda. This is the rate at which we're leaving the state. And then the kind of subdiagonal, we have lambda, because this is the sort of probability or the rate that we're then coming into our current state from. And we get the same sort of matrix differential equation system in the bottom, so that the sort of time derivative is just this matrix times the initial state, and then the solution is then the exponential of this. So as I kind of pointed out, and you've probably noticed, the matrix is very structured. So all of the rows are basically the same, except the kind of one row is just the previous row, but sort of shifted and kind of wrapped around the previous row. And this is called a circulant matrix. So the first row really sort of defines all other rows, as I said, because of the kind of cyclical nature. And this is actually quite an interesting sort of property or structure mathematically. And so the really cool and convenient thing for our application is that circulant matrices have the same eigenvectors for any circulant matrix. And so the eigenvectors are coming from the sort of Fourier matrix here. And so this maybe shouldn't be very surprising, because we have this sort of cyclical nature of transitioning through the states, and the sort of transitions into and out of a state isn't state dependent, right? If it's in state 5, then I had to have come from state 4 and I'm going to either state 0 or state 6, depending on how many players. That's the same as if I'm in state 1. And so it's probably not surprising that sort of Fourier transforms and sines and cosines pop up. As we saw in the 3-player case, we get decaying exponentials and then sort of sines and cosines that are giving us these oscillations. So since we just can automatically write down the eigenvectors, and in fact, the eigenvalues have a nice form as well, given by mu on the right, it's really easy to diagonalize our system. And once we've diagonalized it, then basically we can kind of distribute the exponential, matrix exponential through the diagonalization. And then we just get kind of the element-wise exponential of the eigenvalues. And then we just have a simple sort of matrix vector product to give us the probability at any particular time t. So we're not going to write out the full sort of sine and cosine and exponential decay expansion, because it gets a bit messy for many players. But these are what the graphs look like in the end. So on the left is the 4-player case. So as Matthew described, P0 is sort of always going to be best for very low rates lambda, just because that's the state you're starting in. And then unsurprisingly, the sort of the kind of ranking, if you will, is then player 1, player 2, player 3. But then once we get to sort of lambda is about 1, player 1 becomes the most likely to win, overtaking player 0. This maybe isn't surprising. If you sort of expect one goal, then having one goal is sort of the most likely. And then sort of between 1 and 3, we have these sort of transitions, and it's not obvious sort of which player is best. And then after about 3, there's not much advantage for any player because of the exponential decay. And it sort of turns into a completely fair game. So similarly, on the right is for 5 players. And again, we have the same kind of behavior for small lambda values. The ordering is sort of just the natural ordering because there's not many goals scored. But then sort of, again, between kind of 1 and maybe say 4 now for lambda, we get to see a lot more of the kind of sine and cosine nature of the problem. And so there's a lot more sort of crossing, there's a lot more variation, and it's definitely not obvious sort of which player is going to win or is more likely to win, rather. So naturally, what we might want to do is actually compare this to some real data. We've sort of set up this model and done some analysis and made some claims about who's more likely to win. But we haven't actually decided if it's a good strategy or a good model. So this graph here is the purple bars are from Premier League data. So we had, I think, 22 years of Premier League data. And we just sort of added up the total score to give us the number of goals. And then the green line is the kind of Poisson distribution with the lambda picked based on the average goals. So the average goals, I think, was about 2.7 goals per match. And so we can see that this lines up quite well. So for 0 goals, it's a bit more likely in the data than what the model predicts. Other than that, the rest are pretty closely matched, particularly for the higher numbers. And so the fact that the sort of distribution matches our Poisson model means that we probably have a good sort of model for how likely a particular winner is. So we're going to go back to the 2 and 3 player case and just see how our model compares to the actual data from 20 years or so of Premier League scores. So on the left is for 2 players again, and the top is the graph we saw earlier, just the kind of exponential decay to a half. And then the bottom table, we have sort of the probability of the even player winning and the odd player winning, and the data versus the model. So for the data, it's a little over 51% of the time there's an even number of goals, whereas our model predicts just slightly over 50%. And so it matches pretty closely. The data is a bit more sort of exaggerated. There's a bit more of an advantage in the data than in the Poisson model, but it's reasonably close. And just as a kind of random comparison, in the data, there being an odd number of goals is pretty much the same percentage of you winning a game of roulette just betting on black or red. And so there is sort of an advantage for even, but it is quite sort of close, reasonably fair, regardless of which of the two you end up with. On the right is for 3 players. And so here, the data and the model match actually quite closely. So both P0 and P1 are actually quite close. So in the data, just under 33% and a little under 35%. The model is only sort of 0.2, half a percent or so off. And then P2 has a noticeable or a slight disadvantage, a little under 33% as well. Oh, and I should say, the dotted lines in the figures, which we haven't talked about, are the sort of scoring rate at halftime and full time. So as I said, around sort of 2.7, this is kind of sort of what sort of regime of this plot we're in. And so at full time, it's quite close, quite fair, sort of. The data we found also had the halftime scores involved, in it rather. And so we could do the same thing, but only looking at sort of the first half of the football matches. And here, the observed and the predicted line up almost exactly, at least sort of by eye. And there's a few factors that we thought might contribute to this. So in the second half, players start to get tired or subbed off. Managers might have different kind of strategic decisions, or whether or not they're going to sort of try and stretch out a game for a draw or try and push for a win. So we thought there were potentially a lot more sort of external factors later in the game that might affect the kind of distribution, whereas these we didn't think really played much of a role in the first half. Right. So again, this is the same sort of setup, but now we're looking at the halftime results. So now kind of the left dashed arrow, dashed line. And so now, again, the model and the data are quite closely aligned. There's about 0.5% difference. So about 55% in the data, the even player wins, and about 54.7 or so percent is predicted by the model. And this is a reasonably noticeable advantage now. So this is sort of 5 out of every 9 games you would be correct. And then on the right, we have the 3-player case, and this is perhaps more interesting. So P0 and P1 are quite closely matched, quite even. So in the data, there's about 1% difference, and in the model, there's less than 0.5% difference. So player 0 and player 1 are actually quite evenly matched in the 3-player first half version of the game. Player 2 has a large disadvantage, only about 22% of the time in the real world winning, well, and in the model as well. So we've also sort of wondered what might happen in other leagues, or are other leagues, do they have different outcomes? So there's quite a lot going on this plot. I'll try and walk us through it. So this is the same plot we saw before for the 5-player game. So the 5 lines of the 5 different players. I've sort of zoomed in to the region lambda is between 2.5 and 3.5, just because this is sort of a standard goals per game in football. And we've looked at the top 5 leagues, the top 5 men's leagues last season, as well as the women's league from last season and the women's Euros, which was just a month or so ago. So the Italian league had the lowest goal scoring rate at 2.55 or so. The Spanish league was just slightly higher. And then about a third of a goal higher than that was England and France. They were quite closely matched, just under 3. And then a little bit above 3 in the highest of the men's league was the Bundesliga in Germany. And then a little higher than that is the WSL, which is sort of the women's version of the Premier League. And then women's Euros had over 3.4 goals per game. But there's some sort of caveats with that, if you will. And so even across different leagues, we get different sort of results or who's more likely to win. So there's kind of 3 regimes or 3 sort of orderings of the players. So the Italian and the Spanish league, so the results go sort of player 2 and then player 1, player 3, player 4, player 0, sorry, and then player 4. And then shortly after the kind of Spanish goal scoring rate at around 2 2/3, sort of player 1 and player 3 swap and player 0 and player 4 swap. And then this stays the same for the Premier League, the French League, and the German League, as well as the sort of the WSL. And then now player 4 and player 1 swap, and player 2 and player 3 swap. And then we have sort of the goal scoring rate at women's Euros. And so a couple interesting points in this. So player 2 goes from, player 2 is the most likely to win in the top 5 men's leagues as well as the WSL, which maybe isn't that surprising, but it's sort of interesting that it kind of is the highest over all of those leagues. Player 1 starts out as sort of the second best in the Italian league, but by the time you increase the goal scoring rate to what we saw in the women's Euros, it's actually now the second worst. And so we thought that was quite interesting how sort of comparing even just 2 sort of leagues or a league in a tournament, you can get vastly different sort of, or you can get large differences in the order. It may only be sort of a 5% difference in how often it wins, but the kind of ranking is much lower, which we thought was quite interesting. So another thing we thought a little bit about is how this might apply to other games. So football is probably the most interesting, mainly because it's quite low scoring. But other games have some interesting properties that we've very briefly looked at. So one example is basketball. So there's sort of 3 ways you can score points, or sort of 3 different point totals you can score. So a standard sort of 2-point field goal, which is about 2/3 of the field goals. You can get a 3-point field goal by shooting from farther away, and that accounts for about 1/3 of the field goals. There's also a way to get a 1-point free throw, but we're not really going to consider that just because it's kind of dependent on other events in the game. So we're just going to ignore that for today. And so the interesting thing here is now, so in football, you always sort of increment the score by 1. And so in our kind of cyclical dynamical system, you're always just kind of going to the next state. But if we kind of keep score in basketball by just sort of taking into account these field goals, well, now we either advance 2 steps or we advance 3 steps. And so that means in a 2-player game, a 2-point field goal is actually sort of meaningless because you sort of 1 point goes to your opponent and then the next point sort of loops you back to where you are. And so you end up with sort of self-loops in the matrix. Similarly, if you're playing with 3 players, now 3-point field goals don't really matter because you just sort of end up back in the same state because the kind of the sort of number of points you're scoring is equal to the number of players, and so you just end up back where you started. And so we can, of course, generalize this in the same way we've done before. So on the left is our kind of colored in matrix from the kind of football version. So again, the purple was sort of the probability of, or the rate of leaving a state, and then the green, which is on the subdiagonal, is sort of the rate into the state. For this kind of modified version for basketball, we still have this sort of purple diagonal of us leaving the current state, but now we have this sort of blue color, which is the rate of scoring a 2-point field goal, is now kind of on the second subdiagonal, and then we have the green ones, which are the rate for scoring 3-pointers, which are on sort of the third subdiagonal. And so we get this more sort of interesting structure. It still has the same sort of core property of it being circulant. So every row here is still sort of the same, but kind of looped around. But instead of having this kind of bidiagonal matrix, we now have this sort of less trivial banded matrix. But again, because it's still circulant, we can still just kind of quickly find the sort of state after a particular time because we know what the eigenvectors are, and we can just sort of read off the eigenvalues. So as I said, this is sort of more interesting mathematically because the matrix is a bit more interesting. The solution, I guess, is still quite similar. However, the kind of issue with basketball is that it's very high scoring. So last year in the NBA, there was about 28 2-point field goals and about 13.5 3-point field goals. This is combined between the two teams. And so if you remember back to some of the plots, once we were at a lambda of maybe 3 or 4, we were sort of saturated and it was a fairly even game. And so this is well past sort of that point where you're going to have noticeable differences. And in fact, in the bottom here, I've computed the sort of probabilities, even sort of dividing the rate by 4. So we're considering this on a quarter by quarter basis, sort of like what we did looking at just the first half. And you can see for a 4-player game, it's basically within 0.03%. And so, I mean, that's pretty much about as fair as it's going to get. And again, this is only for 1 quarter. An interesting thing, I think, because it's 4 players and you in some sense have different kind of orbits almost. So if you score consecutive 2-pointers, you go kind of like state 0 to state 2, back to state 0. And so you can kind of loop back in a kind of faster way, if that makes sense. And so P0 and P1 here, P0 and P2 here have the same probability, and then P1 and P4, P3 have the same probability as well. Again, because you have these kind of, because there's now multiple sort of trajectories through the sort of network, if you will, we get this kind of difference or sort of similarity between some of the states. And then the last one is the result for 5 players. And again, it's sort of 20% across the board within 0.03 or so. So this is a very fair game, which if you're doing this as a sort of proxy for a coin flip is probably or a dice roll, this is probably a good method. If you're trying to slightly swindle some of your friends, then it's probably less effective. So just to kind of wrap things up, so we've modeled goal scoring as a Poisson process. We can easily estimate probabilities of winning in a 2-player game, 3-player game, even for an n-player game. It's very efficient to just kind of compute the probabilities. It's just a single matrix vector multiplication. We found some Premier League data and sort of, I was going to say fit, but we sort of computed our model with the average, with lambda based on the average from the data, and it fits the data quite well. So we're able to sort of predict how often a football game in the Premier League will be even or odd scoring or other sorts of parities. Higher scoring gives a more fair game. So unsurprising, the more you sort of score, the more you kind of loop through the sort of network, and so that you get a kind of higher variance and spread across the states sort of faster. And so we sort of briefly looked at sort of more complex games. So we talked a little bit about basketball. This is probably a very fair game because it's one of the highest scoring sports. We haven't talked about it today, but Matthew and I briefly talked about a sport like baseball, which we think is interesting because time is in some sense discrete in that. So you don't have a clock that's ticking down. You have sort of a number of players or batters that the game sort of lasts through, and so you get kind of discrete time instead of continuous time. I don't think we're sure how the model changes or how you handle scoring in this, but there's definitely other kinds of games where there's sort of similar processes that would be interesting. So I think I'll stop here. I think that was sort of everything we wanted to talk about today.
Fantastic. Thank you very much. I'm going to try and use the clap emoji. Hey, there it is. Thank you so much for that. So we have some time for questions. Everyone in the room, you're welcome to pop your hands up, pop questions in the chat, and I'll read them out. But whilst you're all thinking, I'll start with one as well. I think this is a very inspiring talk and a really good demonstration about, how maths sort of used to be. This idea of, being an amateur mathematician and being a polymath. These are the sorts of problems that people solved, like hundreds of years ago and stuff. And a really good demonstration of what captures maths today and the Graham Hoare Prize. And I think why I like it so much is because now you've presented it, I'm like, that's so obvious. I could have thought of that as well, but I didn't, right? And so what I want to sort of like try and tease out is, how did you settle on the Poisson idea? How did you settle on the dynamical system? What was your thought process about that?
I don't know if Brady's going for this or you want me to comment.
You've unmuted now, so I think you need to go.
You can both comment if you want.
Yeah, I mean, I think yeah, I don't know how to take the fact that this is obvious, but no, I'm joking. I think that
in a good way.
I think that oftentimes people so I think with this example of the kind of the Poisson process and then thinking about it as a dynamical system was actually we did the bet, and that was kind of one thing. And I was actually teaching a course that had some that was looking at just modeling time evolution of systems. And kind of the same solutions started to pop up. And so I then realized that some of these slightly harder sums, so the 3-player case, could actually be solved much more easily if you did this time evolution system. And so I think yeah, Brady and I used to talk a lot about these types of problems. And so we kind of had the 2-player case worked out, and we briefly mentioned some stuff. And I think then that problem was just hanging around until the kind of, oh, it was quite neat came along. So I think that's, yeah. And maybe if Brady has something to add to that.
Yeah, I think the way we sort of presented it here and talked about it in the article is quite, as Matthew said, sort of how it actually went. We sort of did the 2-player case and worked out some of the math. And then I think we solved the 3-player case with Mathematica, but we didn't know how to do it like evaluate the sum by hand. And then I think for more players, Mathematica didn't spit anything out or something. And then, yeah, Matthew was sort of teaching a course and then kind of went, oh, wait, we can just sort of write down this sort of network flow problem. And I think for your first point, Poisson processes appear a lot in anything you sort of count. So like number of earthquakes in a 50-year period or anything sort of like that. So as you say, I think it's sort of obvious to try. I think it worked a lot better than what either of us expected.
Yeah.
But it was quite nice that it did actually sort of work out.
Yeah. Yeah, but when I meant by obvious, I mean, now that you've done it, I'm like, oh, of course, that's what you do. If I was you in the moment, I'd have no idea.
Yeah.
What's so nice about this talk is that the maths is very complex, but now you presented it, I'm like, oh yeah, that would be a really good idea to do. So thank you for humoring the question. And so I think there's a combination of being intrigued and well-read is where you had this problem that you came up with, solved it in a way which was natural, read around a bit, was doing some teaching, and came up with this other idea. I think if I was you both, I think I would have brute forced it, like got into Python and just slammed it in there and seen what happened. But there's no joy in that. Well, there's joy for me because I get an answer, but there's no joy in this sort of thing. So yeah, I'm not surprised Mathematica struggled. Well, actually, I am a bit surprised that Mathematica struggled from 4. When you did the 3-person, did it actually give you the formula, or did it give you an approximation? Do you remember?
So I think it may have worked for the larger player cases as well. I don't remember. For reasonably small matrices, it can just sort of brute force the matrix exponential, even symbolically, just because it kind of like can diagonalize and compute the eigenvalues. And so Mathematica does give the full kind of like sine and cosine sort of expansion, or at least sort of in terms of like complex exponentials. But I don't think unless you like tell it that it's circulant, Mathematica will necessarily check. And so then it's just trying to diagonalize like a 10 by 10 matrix, which isn't particularly trivial.
Yeah.
Necessarily. But yeah, I think it sort of could do the higher, but I think we just got bored waiting around.
I think the sums it stopped evaluating fairly quickly.
Yeah, I can imagine.
Direct expansion, directly explicitly asking for it to evaluate the sum was like 3 or 4. It couldn't evaluate that.
Yeah, no, I can completely understand that. So we've got a couple of questions in the chat. I'm going to go to Yihi first. I'll read them out since we've typed them in. So can you comment on the difference instead of the sum of the scores? Does that question make sense to you?
Are we saying reds minus blues? Is that what we think that?
Yihi, if you can, do you want to come in and say something? Because
I mean,
I understand the question either.
I think
Hi,
is that
can you hear me?
We can hear you.
Sorry, I cannot turn on my camera. I don't have it. So basically, I'm talking about still maybe in terms of a 2-player game can have bet on the odd or even on the difference between red and blue points. Yes.
Yeah, I can maybe comment on that if that's okay, Brady.
Yeah.
So if I try to go back to the diagram, I think it's going to work out very similarly. So if you consider this kind of diagram on the right of you have the even goal difference and an odd goal difference, I think every time you score a goal, you'll change the difference by 1. And so you'll continually flip between the parity. So I think in essence, that should be exactly the same solution. Off the top of my head, I mean, Brady.
So I think for 2 players, you're correct, because basically if I have an even sum and I'm sort of getting to it by adding 2 numbers, they're either both even or both odd. And so I think the difference and the sum have to have the same parity for 2 players.
Yeah, I think that's the case. And then in the 3-player case, you'd basically have you could go backwards on the plot. So because in the 2-player case, you effectively have I don't know if my cursor is shown, so I'll just try and explain it. You basically have even to odd and odd to even. But in the 3-player case, you'd have, obviously those arrows can go both ways, but that doesn't change the kind of network topology in the 2-player case, but I think it would in the 3-player case.
Yeah, because in the 3-player case, you'd have kind of like lambda and then like lambda prime or something. So there would you would kind of have the like different rates for different teams, which is one thing we sort of wanted to avoid.
Yeah.
I can smell a new Maths Today article.
Yeah, I guess if we assume the rates of scoring is the same across all the teams, and even the lambdas will stay the same.
Yeah, I think in that case, then the matrix at the bottom just sort of becomes symmetric.
Yes,
right? Because it's sort of no longer directed, I think.
Yes, very sensible. Yes. Yeah, I'm actually thinking of a problem of how multiple ants decide to move a larger object, because there are some kind of observations suggesting somehow they arrive at the object and trying to move around the object rather in random direction. And then after a while, there will be a kind of deadlock period. And after a few seconds, some will give up and they somehow arrive at a consensus and move in one particular direction. So when I was looking at this paper, Poisson process directly came into my mind, but then I realized that in this process, maybe this kind of difference between random agents trying to pull into one direction is more sensible. But then then somehow I was lost in the maths. So your talk is very inspiring. Thank you.
Thanks.
Thanks. Yeah, it sounds like a cool problem as well.
Yeah. So second question in the chat from Luke. So does the person picking n-1 ever have the best probability?
So I think technically, but never like a sort of non-negligible amount. If Matthew, if you go to the like 5-player game, I think there's like a tiny little part where it's the highest. Yeah. So I think at like between 5 and 6, yellow I think is the highest. But I mean it's quite a small margin by the time you get out there.
Yeah, I think that's the case. And I would be very surprised if I was playing this game and someone picked n-1. I think they for sure want to lose. Does anyone else have any questions for Matthew and for Brady? I'll let people type for a second. Yeah, I thought someone might pick this up. Thank you very much, James. So I'll read it out for you. You said there was a caveat for women's Euros. What was that caveat? I think I know what the answer is, but
so there's kind of two, and I don't know which one's necessarily more important. One is there's very few games. So I think there was only 31 games in the whole tournament, whereas a Premier League season has 380. So I don't know how sort of accurate in some sense that number is. I didn't look at any other tournaments. Even the WSL only has about a third as many games as the Premier League. And then the second one, which again, I haven't tested it, how much it makes a difference. Several of the knockout games went to extra time, and several of those games had goals scored in them. And so like 5 or something of the games were 120 minutes instead of 90 minutes. And there was like, I did 4 or 5 or something goals scored in extra time. And so I didn't do any kind of like normalizing or anything. I just sort of did goals divided by matches. But that's going to slightly skew the number to the right, just because there's sort of 4 or 5 goals for free or whatever it was.
There was a lot of extra time goals, which worked well for us. And that's the recording. So whilst anyone else pops questions in the chat, I have my final one for you both is, do you want to say a little bit now about what you're doing?
In terms of the day-to-day?
Yeah, your role now. How have you progressed since publishing this article?
Yeah, so I submitted and finished my PhD. So that was a big life moment. And I'm now doing a postdoc. I'm in the Department of Chemistry at the University of Cambridge. So moving more towards the application, but it's quite fun because we get access to lots of interesting experiments and lots of data that keeps popping up. So I'm really enjoying this.
So I submitted, what was it, a week after you submitted?
Something like that, yeah.
And then I had my Viva a couple months after you did. So I'm also all finished. I don't currently have a postdoc, but I'm applying for postdocs and looking for things. And right now just trying to finish off some side projects and papers from my PhD.
Yeah, it's now a good time to be doing that. I certainly remember the stress being over and finishing up stuff. Well, congratulations to both of you on finishing and obtaining your PhDs, and also congratulations again on the awards. no one else seems to have any questions. So I think let's go and enjoy the sunny day that's left over. Hopefully it's sunny where you are. Everyone in the room, thank you very much for coming along. Hopefully see you in the next one. The next seminar will be in October. It should be going online shortly. It will be the 2024 Graham Hoare Prize winner to talk about their work, which is also available online. Hopefully see some of you there.